All right, so let's try another example problem, this time one that involves both forces and motion together, kind of pulling together our two units. And this one also is going to demonstrate how to solve problems that don't give us real numbers, just give us variables and these kind of factor of change problems. So we're bundling a lot of practice into this one problem. But the problem solving strategy stays the same. And that's one of the big takeaways that I want you guys to have is that when you're solving physics problems, you can't always do them the exact same way. You can't just look at a past problem and change the numbers or something like that. But going through these steps and understanding how physics works makes every problem still solvable, even though it looks very new compared to ones we've done in the past. So first thing we're going to do is we're going to draw it. Let's just real quick. We have a car. Uh, okay, we have a car. It has a mass m. It's moving at some direction v, and it takes an amount of time t to stop. It's stopping at the end. Our real question is what happens? Oops, that shouldn't say d there. That should say t there. How would it change t? Sorry about that. And so the problem is talking about, okay, if m goes to 2m, t goes to what exactly? So this is how we recognize that this is a factor of change problem, because we're changing something by a known factor. In this case, we're doubling mass. We want to know what factor that affects t by. So we've drawn it out. We need a free body diagram. We have a car. It's going to have its own mass, its weight pulling it down. It's going to have normal force that's equal in magnitude because it's not accelerating vertically. All of the accelerations happen horizontally. So these are the same forces or same magnitude forces, just opposite. One's going down, one's going up. And then we're going to have friction slowing it down. The friction of your tires on your road is what brings you to a stop. So we have friction bringing us to rest. And that's it. We have no forward force. The only force that can act on cars is either speeding them up or slowing them down or turning them, but it's all friction no matter what. And in this case, we're slowing down, so we're going that way. I need a coordinate system. Let's say that for now, going in the direction of the motion is positive, up is positive, and we'll say the initial position of the car is 0, 0. Okay, so we need to set up our symbols. That's all of the forces, mass, and acceleration. So the forces that we're looking at here are normal force, weight, friction. We could put F net on here if we wanted to. And then we have mass and acceleration all going on here. And then we also have all of our kinematic variables, x naught, x, v naught, v, a, and t. Just a reminder, these accelerations are the same. And that's going to be really relevant to us in this today's problem. So going down and figuring out what we know that mg is actually equal to capital MG, because we're just plugging that in. We know force. Okay, we don't know what it is, but we know it's going to be the same. So let's just use this placeholder variable of F to go in there. Our net force, we have no vertical forces going on here. They're going to cancel each other out, but we do have F as our net force. Our normal force is also going to be capital MG, or I guess maybe it would be 2mg if we're looking at the other part of the problem, but it doesn't really change things. We have either m or 2m here. Okay, we don't know what the acceleration is yet, but we're probably going to need acceleration in the same way that we often needed time in our projectile problems. All right, going up to our kinematic variables, because I said this was my initial position, my x naught must be 0 meters. My final position is unknown, but we may not need this. This is asking about t, not d anymore. So these variables actually we can get away with not using. There's no reason for us to talk about position if the question itself doesn't mention position. All right, our initial velocity is going to be v. That's a placeholder variable because we know it's starting at speed v. We don't have a number for that, but we can keep it there. Its final speed will be 0. Okay, it's going to have some acceleration, but we don't know what that acceleration is. So we, again, will be solving for that. And then we have time t, but we're really trying to figure out what time changes to when we double the mass. So this is the one that we're really trying to figure out. We'll have to figure out acceleration along the way. And the only other thing that I want to kind of mention on here is I need to be careful with my signs, which I wasn't when I first did this. My net force actually needs to be negative based on my coordinate system. I said this direction is positive. The force of friction is in the opposite way, so it needs to be negative when I set it up in there. Okay, so we got all that. Now let's start solving and start using some of the equations that we have to find the unknowns. First one I'm going to try and use is acceleration equals the sum of the forces over the mass. And I'm actually going to be good to go, I think, because we know that the net force is negative F, and we know that the mass is either capital M or 2m. We'll just leave it as m for now. So I know the acceleration now. It's negative F over m, negative F over m. Sure, that's not a number, but it is something in terms of variables that we know we either know the value of or we know they're staying constant. So now I can use a kinematic equation. I know velocity stuff, I know time stuff, I know acceleration. That's looking like the first kinematic equation, v equals v naught plus at. But I can substitute in that acceleration that we just got. I can also cancel that out because it's 0. So we get 0 equals v, this is becoming v from there, minus f over m times t. Well, I'm trying to see how t is going to change, so let's get t by itself by adding this f over m times t to both sides. So I get f over m times t equals v, because I added it to both sides. That got rid of it on this side and put it over here. And then let's multiply both sides by m and divide both sides by f. Basically, multiply by the reciprocal in order to get rid of that's mass on the top, mass on the bottom, friction on the top, friction on the bottom. We get t equals v times m over f. And so now we can start plugging things in. We can use that factor of change method that I've mentioned a few times. I know that v isn't going to change at all. It's the same v in both problems because we said, okay, same initial velocity. So factor of change there was 1. Factor of change of the mass, well, the mass is doubling. So that's the factor of change right there. The factor of the change on the braking force, well, that's remaining the same. So 1. So when I evaluate that, I find out that it comes out to 2, which tells me that the final t is going to be 2t. It will take twice as long to stop if the mass of it doubled. Okay, that's not a huge surprise there, but we have to prove these every single time because it's not always going to work out that easily. So that's how to solve this problem. We used the factor of change. We used free body diagrams. We used kinematics equations. We kind of did everything that you should know by this time in the unit. So we'll practice this more in class, but here's your example problem. Hope it helped.